Good morning, everybody. Welcome back to another episode of C versus C++ in the embedded ESP32 world. So I filmed one of these a while back with the intention of doing them more often. And as usual, I didn't do it more often. But the purpose of this, if you missed the original stream, is that I'm a fan of C++ over C. I've done both quite a bit in my career. And as I've gotten more horsepower and flash size and things on embedded systems, when I can, I prefer to use C++. And I've seen things and learned things about zero cost abstractions where there's no difference between C and C++, but I don't fully understand where those trade-offs are and which, you know, containers and algorithms and things like that. And so I was just going to run some basic tests with C and C++ side by side in ESP and learn more about the trade-offs, and I figured I'd film it as I went along. So this is what you're looking at is the state that we left off in last time, which is I have a main.c, which is C code, and I have a main.cpp, which is C++ code. We're basically modifying both of them side by side to see how they differ. We build them and then we compare the difference. And so I've got the difference showing down here. I showed how to do this in the last stream, how you can take the map file from one build to the next build and compare them, and it'll show you like this is how much more DRAM or less DRAM you're using, IRAM, flash size, and all of that. And so this is the output. You can see it says anywhere it says current is referring to my CPP map, so that's the CPP build. And the reference is the C. So they say the difference is current minus reference. So all the numbers will always be shown as the C++ minus the C. And as you can see here, Bellum, what's up? How's it going? As you can see, in this very, very simple, contrived example of having a main, looping forever, and printing a simple string, they're identical. There is no difference between the DRAM, the IRAM, and even the flash size, which surprised me a little bit because if you count, this string right here is actually one character longer than this one. But I guess however it gets built and stuffed in and linked together, they turn out to be the same because the text and RO data, as you can see here, are exactly the same size. There's no difference. These compile to exactly the same size and perform the exact same function, which is to just infinitely print a string. So that's our baseline. And just as a quick refresher, where run experiment. This is the script that is running. Not a lot going on here. It's just I clean out the results folder. I make it again. I do a full clean. I do a build with C version equals 1, and that's what triggers doing all the C building. And then I go and I grab the map file and I run a size components. I do a clean, and then I do the whole thing over with CPP version equals 1. And then at the very end, I just run idf size.py diff right down here and store that in the diff file, and it gives us a difference between the two. Now, what we'll do eventually with this, I'm hoping, is to actually, right now we're just looking at the sort of compile flash size and things like that. As it gets far enough along, I want to compare things like heap usage, memory, things like that. Right now, I can't. It's one of those, I'll taint the test if I put too much code in to profile the runtime. And so I'm going to work at this very low baseline, kind of build up, and then eventually hopefully get to a point where we can say, all right, now let's run this on hardware, see the memory usage and things like that, and then in the C version and then the C++ version, and compare those as well. And so that's what we're doing. So I'm going to close that. I'm not sure why it closed my main. Let's see. Split right here. Okay, so what are we comparing today? Should have left off with that. Today, I want to compare threads and sleeping. So this is one of the things that I think you get used to an IDF, but I hate the syntax for doing threads and sleeping. And I use it extensively in another project I'm working on, all in C++, but I don't really understand how much of a trade-off I'm making in doing that in C++. So today we're going to get some hard numbers on that. So let's jump into it. Okay, so the first thing we're going to do, and for any testing that I ever do run on hardware, it's just this dev kit C. So nothing special, no special hardware here, just a simple dev kit. It's not uncommon to take a program like this. So right now, this is perfect. They're exactly the same. And so we have a great baseline to compare. And what we're going to do is just, instead of printing this as fast as the processor can do it, let's add a delay here. And the way we do that in straight C, ESP-IDF would be a v task delay. And I'll just come down here and show it. It's this v task delay, and then you have to give it this const tick type ticks to delay. This is a common way to do that. So we'll just copy this here. And so we'll say, paste that in. Let's not do 500. Let's do 2000. Okay. And you'll see that it's not going to build because it's saying, I don't know what port tick period millisecond is. And so let's get out of this here. And so we need some header files. And I believe it's include FreeRTOS. FreeRTOS.h, I believe is what we're looking for there. And we can test this. We can do C version equals 1, idf.py build. So let's get this to build first, and then we'll worry about. Okay, so that looks like it worked. Just for kicks, let's flash it. Flash monitor. I have two USB things plugged in. Hold on. I got another dev board hooked up over here, so I need to swap these. Okay, I think that's gonna work. Okay, and then this should just say I'm the C program every 2 seconds if we've done this. Oh, not every. Oh, that's saying I'm the C++ program. What did I do wrong? Obviously something. Okay. I did C version equals 1. Let's look at our CMake list. If env C version, C underscore version. Did I spell it wrong? Oh, I know why. I know why. I got to do a full clean. Once it's already built, it's not going to redo it again. So let's do this. C version idf.py build. And I have a little output here that'll tell you which version it's building. Where is that? Performing. Here you go. Building the C version. So, and it failed. Great. Because it has no idea about vtaslate, which I thought it wouldn't. So that makes sense. Because we also need to include, include FreeRTOS, I believe it's task.h. And let's try that. Okay, perfect. Now let's do an idf.py flash monitor. I unplugged it. Okay. Okay, I'm the C program. I'm the C program over and over. Great. So that is a simple delay. The raw C FreeRTOS way. Okay, great. I'm gonna cancel that. IDF.py full clean. And now how would we do this in the regular C++ way? Well, we got to include a couple of things here. We need to include thread, and we need to include chrono. These are the two libraries, standard libraries. And again, I mentioned in the previous stream, one of the things I really love about doing this in C++ is that this code ends up being very portable. It helps a ton with unit tests because I don't have any of these specific ESP dependencies or FreeRTOS dependencies. Now, when it builds under the hood, those are all there, but I can take this main.cpp, bring it right over to a regular machine, compile it and run it and get the same output. And that to me is pretty cool, and especially when you're doing unit testing. Okay, so what we would do here is we would do the standard, this thread, sleep 4, standard chrono, seconds 2. Okay, and you know, we're dealing with very low number of lines of code here, but for me personally, I love this a lot better. And you can do using namespaces, so you end up just writing things like sleep 4, seconds 2. I don't mind fully qualifying like this, but so this is the C++ version of this that does the exact same thing. And it's a little more, to me, it's more readable. You might argue, oh, you just get used to VTAS delay, 2000 divided by port tick period ms. I'd like to say this thread sleep for 2 seconds. Like it reads better, in my opinion. Okay, so now let's do the same thing. I cleaned it. Let's do cpp version equals 1, idf.py. Let's just go all straight flash monitor. It'll build. It'll build as part of that. We just need to make sure. Well, I guess we'll find out. Building the C++ version right there. We saw it flash by. Here goes. Connecting, flashing. And I'm the C++ program every 2 seconds. Great. Now that we know that everything is working, I'm going to unplug that. And now what we do is we do run experiment. And again, that's just that script that I wrote that builds them both, compares the map files, and shows us the difference. So let's see. I didn't do this ahead of time. I have no idea how this is going to turn out. I want to say that it's not going to be so different because the compiler is your friend and will do its best to only include the things that you need. So we'll see how that. So after this comes out, what we'll do is we'll actually do a thread test next. So we'll actually have a separate, we'll have 2 threads running. We'll do it the C way and the C++ way and see how those shake out as well. Okay, I think we're done. Great. We're going to clear that. And then I just do a less results diff.text. All right, so here you go. When we talk about DRAM, again, the plus here means the C++ version is that much bigger. So we're using 24 bytes of DRAM. This is BSS. So I guess that's total of 48 used. Static IRAM. We're using more IRAM here as well. And then you can see the flash size is bigger, significantly bigger, a little under 10, officially 10K. The text size, and most of that is this our data. So my guess is there, and then at the bottom here, it gives you this total image size is 10,792 bytes larger. Okay, so at first you might think that is exactly why I use C and not C++. Stay with me for just a second. Yes, that is more. That is that is part of it. Has to build some of those standard libraries need to be compiled into the final binary. But if you're on a chip where you have, let's say, a rover, where you have 8 megs of flash, even OTAing and splitting that up into partitions where you have like a 3 meg partition, you have 3 megs of flash space, 10K. Now, this, and we'll see this as we go along. I don't know. I'm just guessing here. These hits aren't going to be for every line of code, right? It's building in. Now, if I were to do 5 more sleeps here, it's not like this grows by 50K. It's there, right? And so it's a lot of these are going to be kind of one-time penalties, and it's a decision. Like, is that 10K of extra flash space worth me being able to write in C++? The answer is always it depends. Do I have the flash space, and do I like the trade-off of writing in C++? In my case, I'm working on, they're 8 meg flashes in one of my projects. And so I have like a 3 meg with the way I've partitioned. I've got 3 megs for each OTA partition. The C++ overhead is not an issue. I've got plenty of room. I'm not even at 50% flash, even in a 3 meg partition using C++. And so don't write it off right away when you see these numbers like this and you get like, oh my goodness, see, this is never going to scale because it's just going to be way too huge. It'll surprise you. It's not going to, it will be bigger. C++ is always going to be bigger, except in those very simple contrived examples that we did. But let's get real numbers around it to see what we're dealing with. So in this case, a simple looping and sleep, we're 10, like I said, it's divided by 1024, so it's not going to be 10K, 9 something K larger total binary size. So, okay, great. Let's, so the question now is, let's see, check it. Oh, you see her. Hey, doing good. Thanks for dropping in. Really appreciate you. Do we reset it and then do separate threads? No, we're just going to keep going because then we're not going to compare. We're just going to keep moving forward. Okay. So let's say we want to have, I'm the C program here. We've got this. The difference is 10,792. Maybe we ought to like just do that. We'll say after simple delay change, we were at plus 10,792. Is that right? Yeah. Okay, so I'm going to keep track of that over here off screen so you can't see that. So we were at 10,792. And you know what? Let's just give real numbers here instead of making them up. 10,792 divided by 1024. Oh, it is. It is over 10. There you go. So 10.5K. 10.5K larger. Okay, cool. Thanks, calculator. All right, let's create another. Let's come down here. idf.py full clean. And let's do a void thread 2 void. And in here, we're going to do the same thing. We're going to say while 1. I'm thread 2. And we're going to do that every 5 seconds. So we're going to kick up this thread and we'll print I'm the C program every 2 seconds on the main thread, and we'll print I'm thread 2 every 5 seconds on the secondary thread. And the way we can do that is, I want to say xTaskCreate. Let's look at the docs here. We give it a name, a task size, idle priority, handle. We can actually send null. Okay, let's just grab this. Okay. And this is well, let's just start with this. Okay, we're gonna say it's thread 2. The name we'll give it is thread 2. Now the stack size. There's a default if you don't specify one in the C++ side. I don't remember what that is, but that's really going to be runtime memory. So that shouldn't affect our build sizes. So let's just say like 4. It doesn't need to be this big at all. 4K. We can say null. The priority, we'll just give it a priority of like 5. In these, the lower the priority, just as a IDF FreeRTOS thing, the lower the priority, the lower, the lower priority it is. There's some programming things where the lower the priority, the higher the priority. So like priority 1 gets more CPU cycles than priority 10. It's the opposite with FreeRTOS and IDF. A priority 5 task will get less CPU cycles than a priority 10 task. So the higher the priority, the more CPU cycles it will get. Okay, we do not have to pass. If you wanted to have a handle to the task, you could pass it there. We're just going to pass null. And I believe that's all we need to do. xTaskCreate. And it should start that thread, I believe. I haven't done this a lot on the C side. I've done this more on the CPP side. So let's do a C version equals 1, idf.py flash monitor. All right, see if that builds and does what we expect it to. Building the C version, great. And all these build times are gonna take longer because, oh, why didn't it like that? Where are we at? Incompatible pointer type. Thread, oh, I think I need to pass this. No, that was not it. Okay, so what, let's actually read the message this time. Incompatible pointer type, aka void pointer. Oh, it's saying void pointer here of like arg. Okay. This allows you to pass context in. Okay, so we should see I'm a C program, and then every few times. Okay, great. So that's working. I'm a C program every 2 seconds. I'm thread 2 every 5 seconds. And that looks like it's working. Great. Okay, so that's the C way. Let's do it in the C++ way. Now, this is done. So IDF supports this. I don't know if it's IDF or FreeRTOS, where you can specify all of these things, but we're going to skip over that. So there's a way using ESP thread to specify like the name of the thread, the stack size, and things like that. If you don't, it's just going to use the defaults. And so I believe all we have to do here is say void thread 2. I don't think we even need to do the void there. And let's just, well, sorry, let's grab it from here. I'm thread 2. And then we're going to sleep this for 5 seconds. Okay. And then down here, the C++ way to do this, standard thread T2, and we're going to pass it thread 2. And then we do t2 dot detach. I think is all we need. I didn't prepare super ahead of time for this. We're kind of just running this on the fly. CPP version equals 1, IDF.py, flash monitor. Let's see what we get. Or if it even builds all the way. Hey, it did. Might have gotten this right the first try. Be a first. Okay, I'm C++, I'm C++, and then you should see I'm thread 2. Awesome. Okay, so identical programs, and you can see so far the code is pretty similar, right? I mean, nothing crazy here. I think it'll get more interesting when we get into some of the things where C++ really shines syntactically over C, but right now there's not a whole lot of difference here. Again, I can't stress enough how much I love that this is not polluted with anything ESP. Like this, we could compile this on your local machine and run it and get the exact same output. You're never compiling this on your local machine because it's going to say, I have no idea what FreeRTOS H is, task.h is, vtask delay. So just going to keep pointing that out. All right, let's run experiment. And this is where we'll end. We'll see what the difference here is. Remember, we were 10.5K larger on the simple delay sleep thing. And now let's see where we end up with the thread difference. Might be able to be under a half an hour in this stream. Be nice. Okay, done. Clear. What am I doing? Less results diff. Okay. Again, we're seeing some minor increases here in DRAM. IRAM, we got a little over 1K, and now we're up to, looks like we're closer to 20K. Let's just do the real math on it. 20 divided by 10, sorry, what am I doing? 2024, 20,024 divided by 1024, 19 point, we'll call it 6. Okay. Okay. And then when we come down here, RO data, so the total image size is that much bigger. So let's just do that one. Okay. Divided by 1024 is 20.98. We'll call it 21. 21K. 21K larger. Okay, so between these two, total flash size difference, we're looking at 21K bigger in the C++ version. So I'm trying to think, is that probably a little bigger than I was thinking, but not much. I wasn't thinking it was going to be crazy, but I thought maybe a little less, maybe closer to like 15 is maybe what I had in my head. So so there you have it. I mean, real numbers difference between running threads. And now, sorry, we got to do one more test, which is, I said earlier, it's not like it increases 10K every time, and it literally just increased 10K. So let's do one more here, which shouldn't need to include any additional libraries, right? Because again, let's say you've got thread 3. Actually, instead of typing it all, let's thread 3. I'm thread 3. He's super lazy. We're going to bring him every 10 seconds. And then do thread 3. Thread 3. Okay. Great. And then let's do the same thing over here. Thread 3. The hope that what I'm hoping to show here is that you won't see another 10K jump. And if you do, then, well, I've learned something. All right, standard thread T3, thread 3, and we'll do T3.detach. For those that aren't familiar with C++, the detach lets the program continue. If you didn't have the detach here, it's going to wait. Well, I guess in this case it might not. It lets processing continue afterwards, and really just like sends it off on its own, because you can do what is it, T2.join. Yeah, it's join, and it's going to wait right there until that thread exits, which sometimes you do, like you send off work to another thread and wait for it to finish. In this case, we want these to just run on their own indefinitely until power is removed. So thread T3, thread 3, T3.detach. Okay, so we've added an additional thread to our program. And I'm not gonna program these. we're just gonna completely run the experiment again. So it'll compile them both and compare the difference. And I'm guessing, let's see, it was 21K larger. Let me put a note here. With threads running, with 2 threads running. And now we'll say blank larger with 3 threads running. I'm not expecting, like, I guess I'm not expecting really any difference, maybe other than like a few bytes, but certainly less than 1K. I don't know. Interesting to think about. Less results diff. Okay, there we go. 21,496, which the last one, and this is where we should write the numbers. 21. I still have it here. 21,488 was the last one. So now it's 21,496. So that's 8 bytes. 8 bytes difference now that we're doing 8 bytes more on the C++ side with multiple threads. So again, that's what I mean when I say one-time hit. Like once you've pulled a library in, it's in, right? And you can use that code everywhere, and it doesn't give you that same big hit every time. And so that was the point that we just illustrated here. Once we had that 21K total hit, and then we added more threads, the difference is negligible. I'd say 8 bytes. And so I'm just going to record this. It is 21,496. It's 21K, 20.99. Okay. Okay. 21,499. What is it? 496. Okay. And sorry, just because you can't see it. Like, there you go. I'm just typing into a document, a text document there. Okay, sweet. That is going to do it for this version of C versus C++. I've got about half a dozen of these queued up of things that I want to compare, like strings are a big one, using char star versus standard string. That one's going to be a big hit, not only in Flash, but also in like memory, because those allocate. But we could do things like array versus standard array. I've got some algorithm ones that I want to go over. I've got a whole list of them, but if there's something specific that you would like to see compared in C versus C++ in ESP-IDF, FreeRTOS using ESP32, stick it in the comments. I am open to ideas that we could learn together with on these to see what the real impact and differences between using C and C++ is in an embedded environment. So I really appreciate everyone watching. Yeah, join us next time, and we'll keep learning together. Thanks.